Okay, so what we're gonna do today is. Let me just- So what we're gonna do today is keep going with this interpretation of a hydraulic head map. So we saw last time this was the map of the piezometric surface, the water table essentially in the High Plains aquifer. And you see the contours here, and they're pretty straight around here, but then they have some curvature, and we want to try to understand that. So last time we went and did some analysis, and we kind of focused in on local areas where we have multiple points. We picked 3 of them, and we came up with this graphical constructions to locate the hydraulic head contours. And what we said was locally, if it was a small area, we could assume that the hydraulic head distribution was planar. And so the contours were straight and parallel and equally spaced. Okay, so that's great. That'll be an important technique for us, the 3-point problem. But in general, contours aren't going to do that. They're going to be curved and not equally spaced, and we want to deal with that too. So what I want to do today is to show you how to recognize different hydrologic features from the contour maps. There'll be things like a recharge zone, discharge zone, gaining, losing streams, different kinds of lakes. And then we also want to be able to make our own contour maps. And so there'll be some general rules of contouring, and I expect many of you, I don't know who's done contouring before. So I'm sure some of you have. And so we'll use those general rules of contouring, but then there'll be some more specific rules of contouring the water table. So rules from hydrogeology that will add on to the regular rules. And then once we make those contour maps of the hydraulic head, we also want to draw in the flow lines, infer some flow path directions for the groundwater. That's what we're gonna do today. So in order to do this, we're gonna have a map, and it's gonna have some contour lines on it, and we're gonna infer some things about it. So I'll bring this up, but I want to just say up front that we're gonna have to make some assumptions. So one of the assumptions is that the hydraulic conductivity is isotropic and homogeneous. Okay, so what we'll see in a few classes is that the hydraulic conductivity can be different in one direction than it is in another direction. Okay, that's anisotropic, and that happens quite commonly. We're going to assume when we're doing this stuff today that it's isotropic, so it's the same, the conductivity is the same in all directions, and that it's homogeneous. The hydraulic conductivity will vary spatially. There'll be different zones of high conductivity and low conductivity. We're going to just ignore that for now. We'll also assume that it's a thin, unconfined aquifer. So it's going to be thin. We're going to assume that it's thin because we're going to be working in map view, and we're not going to really consider any kind of variations with depth. So what we'll be interested in then is just the horizontal component of flow, not the vertical. We'll get to the vertical, but that's not going to be today. So these are some of the assumptions that we're going to make. So what I want to do now is take a look at patterns in the hydraulic head contours and infer what kind of structure is going on. So what I'm going to do is take these contours and use the principle that we developed a while back of the doing a water balance, where we identify a control volume and we have flows going in and going out of that control volume. And we'll use that to try to get some insight. So this is contours. These are elevations. So this is high, and this is low. So this is a dome, right? And so to figure out what this is in a hydrolytic sense, we'll draw in a control volume here at the top of the dome. And actually, let me make it a little bit bigger. We make it control volume like that, okay? And what we can do then is go over to this side, and we can see, well, here's a 10 contour and a 9 contour. So we can draw a flow vector perpendicular to those contours that's going from high to low. So we've got flow going out, and flow going out here, and out here, and out here. Okay, now remember, this is map view, and so these vectors are horizontal flows. So if this is the control volume, and we have flows going out of all sides, then the flow going in equals the flow going out plus the change of storage. I mean, if this were to be, well, from what we can see here, we must have a big change in storage. In order, if the flow is going out, then we must be losing water from storage. But we're going to assume that this is the water table at steady state. So things aren't changing. This is just the way it is. In which case, there's no change in storage happening. And if that's the case, then the only way that we can have this, is if water is coming in from above or from below. Because we have to have the inflows equaling the outflows, right? So this kind of pattern is a recharge zone. So the water is going into the aquifer, and then right here, and then spreading out in these directions. And we can infer that from this water balance approach. Okay, so closed contours forming a dome, recharge zone. Okay, we'll do the same thing here. And this is lower than these, so this is a basin. And we have now flows going in on all sides. So, I mean, if flows were coming, we infer that flows have to be coming in from the outer plane, then here we have to infer that somehow all that water that's flowing in here has to be getting out. So often when we see closed contours and it's a basin or a low point, we figure, well, there's a well right here, and that's pumping the water out. Okay, wells will have these closed contours around them. That'll be in here. We'll also see in a few slides that there are lakes that will do this, but you have to have a way. If it's really a closed contour, you have to have a way for the water to get out. And there are some lakes out west, for example, that have a lot of evaporation, and that's how the water gets out of them. Okay, so those are two examples of these closed contours where we can infer different kinds of features. Okay, so here's a cross section, and we'll infer what's going on here. This is the cross section that I've been drawing really since day one. Here's the water table, and I'm just going to assume that. Let's just assume that the aquifer is like this. Okay, so aquifer is got a uniform thickness, and we're not really worried about what's going on in here. We can say that this is the aquifer. This is where the flow is happening. We're not really having any flow here. So this is the hydraulic head. It just applies to this top surface. Okay, and if that's the case, then we can put in one of our control volumes here, and we can go up here and set the slope, and that's the flow going in. And then here, the slope is a little bit steeper. So if everything is uniform here, the flow has to be a little bit bigger, the arrow is a little bit longer. And then here, we see something similar. The slope is right here it's that, and here, and it's steeper. So what this means here is that we have to have water coming in, right? So that the input's equal to output. And same with this. Okay, so when we see the water table curving like this in cross section, that it's if the flow is going through a uniform layer like this, then the gradient is getting steeper, the flow is getting greater. So we have to have recharge coming into the aquifer. So this curvature here is an indication of recharge. So there. Oh, and then right here, we've got something similar. I mean, if you look at kind of the big picture, the curvature here is negative and the curvature here is positive, right? So what we've got is flow coming here and flow coming here on this side. And so that means that there's flow. You know, if we were to put a box right here, we got flow coming in on two sides, we have to have flow coming out. And that's the flow that's going to the groundwater that's flowing to the stream. Okay, so that's cross section. We can look at this in map view, this interactions with the stream. So here's a set of contours, 10, 9, 8. So this is going downwards. And we've got this V shape. So we can put in a control volume here. And well, we can see that the flow is in that direction, right? That. So we can this is a vector and we can resolve it into components like that and a component like that. And same with like right here, the flow vector would be like that. So there's a component like that. And right here, there would be a component like this and a component like that. Okay, so if everything's uniform, this spacing is the same. So this flow is equal to that flow. This gradient in this going perpendicular to the face here is equal to that gradient, the way I've drawn it. It's supposed to be anyway. So this flow is equal to that flow. And on this side, we've got flow coming in and flow coming in here. So we've got flow coming in on the three sides and flow coming out, but this flow coming out is equal to that flow coming in. So we've got more flow going in than we have coming out in the horizontal plane. So that means that there must be flow coming out vertically. So this is a stream here. These contours are feeding around a stream, or at least that's what we're inferring, because we're gonna infer that there's groundwater flow from the aquifer to the stream. So this would be what's called a gaining stream. The stream is gaining water from the groundwater. Nearly all of the streams around here are gaining streams. So here's the opposite. This is high and low. So we're going now from high to low in that direction. The groundwater flow is like this. So it's away from this zone here. And we've got the flow vectors resolved like that. So if we have a control volume, we've got flow leaving. And in this case, in order to have flow leaving the groundwater in this zone, we have to have water coming from the surface down in, or perhaps from below. But this is usually the pattern that you would associate with what's called a losing stream. So water is flowing from the stream into the aquifer. You see these things out west, in areas where it's dry, the groundwater table is low, or where the groundwater table has been lowered from pumping. And then you've got surface water flowing along, the streams are flowing along, and water from the stream is flowing out and infiltrating and or flowing into the aquifer. So we can identify streams that are, well, then what we could say is in this stream, if we see the groundwater pattern looking like that, in this stream, the flow is expected to increase as we go in the flow direction in that stream because of the contributions from the groundwater. And same here, the flow, or the opposite is here, the flow in this stream is reducing as a result of flows that are lost from the stream and go into the groundwater. Out west, there are streams that are flowing along and then essentially they dry up because they lose all their water into the, well, they're not really drying up. They're not really, drying up kind of implies that they're evaporating, but they're losing the water to the groundwater. Okay, so here's a similar pattern, but it means something different. So here's a contour forming that kind of pattern, and 9. So the flow is like this, and we've got flow. The flow vectors are resolved like that. So this is the same kind of pattern as the losing stream, but this is a ridge in the groundwater water table. So what we can say is that there's right along here, the groundwater is flowing in the opposite direction. And so this is a groundwater divide. We have topographic divides. You can think of this as a ridge that's sloping in that direction. So there's a groundwater divide along this line. Okay, so here's what the groundwater divides often are going to look like. Now here's just an example of contours on the water table. Here's the stream, and you can see the stream. This is the first order stream up here, and they're merging. So the flow direction of the stream is like that. The contours here are pointing upstream. So that's implying that we have flow like that. So the stream is gaining. Same with here and here. And here. And then they curve around like this. And so there's a divide right here. And water that infiltrates here is going to that stream, and here it's going to that stream. You can also infer that this is that we're having recharge coming in here. You know, we saw recharge was a dome, right? But if you have an overall gradient like this, you take the dome and tip it, and it ends up having the curvature like this. So this is recharge coming in and then flowing to these gaining streams. Okay, so the flow goes to streams in some cases, and it also goes to lakes. So there's a couple of different patterns, or a few different patterns that can happen when you have a lake. So here's some contours. Here's 10, 9, 8, 7. And this is the lake here. Lake, the water surface on a lake, pretty much flat. And so the stage of the lake, or the elevation of the water surface, would be the hydraulic head there. So in this case, it's 8.3. And what we'll often assume is that the stage of the lake is the hydraulic head in the lake, and that stage is different than any of the contours that you're drawing. Okay, so it could be that this has a stage of 10, and you have a contour of 10. It could be, but that just ends up being a little awkward, because then you're going to have the 10 contour come and hit this thing. And contours are lines. We think of contour as you have a sloping surface and then a horizontal surface, and it's those two surfaces intersecting as a line. So if this had a hydraulic head of 10 and you had a 10 contour, the contour would be like this, and then it would be this like area. So we don't really ever figure that that's the case. If it's a stage of 10, then maybe it's like 10.001, a little bit higher, a little bit lower. So the contours are not going to intersect the lake. So this will be important when you go to draw your own contours, because you have to have them go around on one side or the other. Now, we can infer what's going on with this lake, because we see that here's the high hydraulic head and low hydraulic head. So in general, we just ignore the lake, we have flow going in that direction. So we can then infer that this whole surface here is at a head of 8.3. So the boundary of the lake would be like a contour at 8.3. So we can draw in, we can say the flow is in that direction here, in that direction, and that it's perpendicular to the boundary. So we can infer that we've got a flow path that looks like that. And then right here, flow is going to look like that. And so we've got a flow like that. And then if we do the same thing over here, kind of like this. So that's the general flow path, just heading along. And then here we can see that the flow kind of curves towards the lake, it goes into the lake and then comes back out. And if we do something similar, we get lines that look like this. And then here, okay. So what we see is that the groundwater here is discharging to the lake, and then it's mixing in the lake, and then around here it's leaving the lake, going into the groundwater. So this is what's called a flow-through lake. The groundwater is flowing through the lake, and it's got a recharge and a discharge zone relative to the groundwater. Okay, so there are lots of natural lakes that look like that. And you can think of this lake as just a place where the water table is intersecting the ground surface, and the lake is really functioning as kind of an integral part of the water table. Well, it's not technically part of the aquifer, because we're going to just define aquifer as being the porous medium, but it's closely connected to the water table, and it has important interaction. Okay, so we probably have some lakes like this around here, but we have a lot more lakes like this around here. So here we've got a stream valley and a dam. So the water is impounded here. And so that makes it a bit different than this, but there are indeed some similarities. We have the stage of the lake here, and we can see that we've got flow going into the lake, and it's going in here and here, here. And then the flow is, or the head is at 7.2, and here it's at 7. So here the head is higher. We've got flow from this point to that point going like that. And, you know, depending upon how this, maybe it's going through the dam, but dams are pretty low permeability, so it might be going under the dam. And if it's really sealed well under the dam, then, you know, then maybe it's doing this. Okay, but there's going to be some flow from the impoundment through the groundwater, and you know, and then entering. You know, maybe it actually comes here and ultimately discharges to the stream. This area certainly will be sealed as best as possible during the construction process, but inevitably there's going to be some groundwater flow that is leaving the lake and entering the groundwater system. So, you know, it's somewhat like this, but really most of these areas are going to be gaining, and then there'll be a small part where the lake is losing into the aquifer down to the dam. Okay. So here's an example of a lake. Well, here's an example of some closed contours that form a basin, and it's not a well. This is what's called an endorheic basin, terminal lake. So the groundwater is flowing into this lake from all sides, and then it's leaving by evaporation. So there are lots of these places in the world. There are not really any of them around here. You can see this map. This is these are the endorheic basins, these dark colors. So out west, the basin range is a large endorheic basin. And what's happening here is the groundwater, there's no surface water flows out of these basins. So Nevada, Utah, any rain that falls there, it's not going to flow to the ocean. Everywhere else here, it's flowing to the ocean, but there's this endorheic basin, and then there's some other ones here in Mexico, and that Atacama Desert in Argentina, in Bolivia. Is one of these basins, and then you can see in Africa and Asia, there are large areas that are internally drained, and the water leaves by evaporation. One of the characteristics of this is that there's very high salt content because the water leaves, but the salt doesn't. So that's certainly something you see out west and the basins out there. Okay. Yeah.
Was there a special name for 2 slides ago, the example on the right, the man-made lake?
Called it impoundment, I think.
It's an impoundment. Yeah, that would be the lake pipe. Okay, so here's the graph that we had on the previous slide. I just took that same graphic and just changed the numbers here. Okay, so instead of flowing to the lake, is now flowing away from the lake. So that means that water is recharging the aquifer. This is a mound here, and then flowing away. So a nice example of this kind of thing is a playa lake. Here's a picture of one. And there are actually many of them here. All of these things are playa lakes. If you go on Google Earth to northern Texas, you'll see many of these things. In dry weather, they dry out and it's just a very gentle basin shape. They get plants growing in them, and they have a lot of swelling clays out there. So when a swelling clay dries out, it opposite of swell, it shrinks and cracks. So when these things dry out, you see just kind of a gentle basin that may have some things growing in it, maybe not, but then when it rains, they fill up and form these lakes. It's actually kind of cool. I did a project out there a few years ago. And these things are pretty harsh, barren looking things when they're dry, not much going on, but there are lots of critters that live in these lakes that go dormant and burrow into the mud. And so they're there hanging out, including these things that look like crayfish, kind of like that big, and also some frogs. So they have frogs that, I don't know, they burrow down in the mud, I guess, and it can be there for years apparently. And then when it rains, they come out. I don't know, maybe some of them are just, yeah, I'm not quite sure about the biology of it. But these things, when it rains, end up just teeming with life. These crayfish end up attracting a lot of birds. So the place where we were had a lot of crayfish in there and a bunch of ducks coming in. And it was just as a result of these big thunderstorms that had come in about a month earlier. So Playa Lakes, recharging the aquifer. Okay, so we can go back now to the map and take a look at, well, maybe some interpretation of these contours. So let's take a look up here. This is up in Nebraska. And so we zoom in here, here's the Platte River. And here are the contours. So you can see the contours are being upstream. So this is the Platte River is gaining here. And we can also go right here. This is the Arkansas River and going into southwestern Kansas. So if you get on Google Earth and go to southwestern Kansas, you'll see hundreds, I don't know, thousands of big green circles. And those are central pivot irrigation systems that take this area that's very arid and make it suitable for agriculture. Each one of those big circles has a high capacity well in the center, pump the water out, and then they put it out in this big irrigation system. As a result of that, the water that would otherwise be recharging the Arkansas River isn't doing it. So the Arkansas River is flowing here, Colorado, and then once it gets over the High Plains Aquifer, it starts losing, and it dries out in many years. So you can see that here. It's hard to see it here, so I blew it up. You can see the contour here pointing downstream. So that's an indication of the river losing water. Okay, so we also want to have evidence for recharge. We saw a recharge zone was closed contours, and we don't see any closed contours here, but we do up there see this. It's not closed, but it's kind of a circle on three sides, or an ellipse on three sides. And basically what this is a dome that's tipped. And you can see the overall slope on this water table. And this is then this recharge dome that's tipped. This is an area of very large sand dunes in Nebraska. You can also see these on Google Earth. So it's sandy, there's the not much that grows there, so it's permeable soil without much growth. So not much evapotranspiration. The water that falls there recharges the aquifer and gives you this pattern. Down here, the contours here are pretty straight. You know, there are some few minor fluctuations, but they're pretty straight and pretty parallel, and pretty uniformly spaced. So if the aquifer here is got uniform thickness, then it looks like the flow is pretty much one direction and pretty uniform. So what we can infer from that is there's not really any recharge going on here. Well, this is North Texas, really dry. And yeah, there's probably not much recharge happening. So we can see now some evidence for these various different features that we saw in an idealized case. Here they are appearing in this real arc. Okay, so we want to go and draw in some flow paths along with contours that we've been drawing. So you saw what I did. I said, well, okay, the flow is going to be perpendicular to the contour here. So, and from high to low. So we can draw these local flow paths. Just the local flow vectors, just drawing them in perpendicular to the contours. And if we say that there's flow that starts here, then we want to draw the flow path from recharge that starts here. So the way to do it is to say, okay, well, at the contour, I know what the flow direction is, and I need to use that as a guide and draw the flow in a smooth curve that where I extrapolate out and have it cross the contour in a perpendicular line. So it's, if the flow starts here, then the contour, I mean, I could say that the contour that comes through here is like that. So the flow is going to start like this, going to cross this contour here, and then looks to me like it's probably going to curve a little bit, so it crosses that contour. So the flow line, the flow path from recharge that starts there looks like that. We do it by estimating the flow path locally, have it crossing these contours in perpendicular fashion. Okay, so when we draw in the flow path, what we need to do is start with a point where we're saying that this is a starting point for our flow path. This is where the water is entering the aquifer, and it gets on the flow path and goes and does its thing. I'm going to have you do this kind of thing on the exam and for homework. Whenever you need to draw a flow path, you're going to have a starting point, and you only draw one flow path. Okay? Starts here and it goes like that. When I get it, somebody will draw. I think what the idea is that maybe you hedge your bets and you draw in many flow paths coming from one point. Okay, can't happen if it's just an arbitrary point in the aquifer. Okay, that if it's maybe like an injection well or right at the pinnacle of a recharge zone, you might. Let's just figure for our purposes here. You have one location, you get one line, one flow. Good. Okay. So isotropic homogeneous flow vectors are perpendicular, and then the flow paths need to stay perpendicular to the head contours. Okay. All right. So what I want to do is to draw in these contours. We saw how we can use them to interpret the flow paths and interpret various different aspects of the water table. So we want to be able to draw our own contours. And want hydraulic head contours and flow lines, identify recharge and discharge areas, find the stream, find a well, and then the capture zone of a well. That'll be the zone where all of the recharge to the aquifer ends up going to the well. So that's the zone where the well is capturing all the groundwater. So we need to draw in the contours here. So here's the approach that I would recommend. So you're gonna plot the location and values of the heads on the map, like we just showed. And then we need to come up with what a contour interval is. So we're gonna go and divide up. And we're gonna select like 5 to 8, or I think on the handout it's 4 to 8 intervals that will be the contour values that you'll use. And the way to determine that is to look at the max value and the min value, and divide that up into rounded intervals. So if the max is 100 and the min is 0, then I would go with an interval of 20. Okay, that'll give you 5 different intervals, 5 different contours. That's a good number to start with. If you did it every 10, you'd have 10 intervals. That's more detailed, but it'll get cluttered. So if you go, we can always draw in more contours. So we can always go for 10 if we want, but I would go and 5 to 8 is 4 to 8 maybe is usually going to be a good number. So then we locate the maximum point and interpolate between the maximum and the adjacent measurement to get a contour line. I think actually I messed up because you have that handout, right? That it looks like this handout here. No, not that one yet. Let's just do this one for now. All right. So let me just draw a sketch of this real quick. So the max is 100 and the min is 28 here. And so I think I would go with 20 as the initial contour interval. Okay, so we can think of this as like a 3-point problem, right? So this is the maximum point. We probably won't have a contour through that. The next contour would be 80. And so 80 is going to come through here, and it's going to come through here. So we could get out our engineer scale and we could go and measure it out and interpolate and get it accurate. But you probably can just go and estimate it and have it be accurate enough. So here's 60 and here's 80. We're drawing the 80 or 100. We're drawing the 80 contours, so it's going to be halfway. So it's going to be there. And then there'll be 80. We'll also have 60 and 40. So there's 80, 60, 40. Roughly evenly spaced. And so there'll be 80 and 60 here. So there's 80 and 60. Okay, so we're just interpolating between these points and determining the locations where the contour is gonna come through. So then we can draw it in. Here, and 60 would be like this. And 40, let's see, we've got 50 here, 30. So 40 is gonna be here, and it's gonna be coming between 50 and 30. And then there's a 38 over here. So the 40 is gonna be like that. Up from 38 and up from 35 and between 30 and 50. And then it looks like we can also draw in a third. So 30 is going to be like this, and then like. Okay, so we can draw them in, and I like to label them. So to label it like on break, or just label it like this. Okay. So we've interpolated, we replete for other contour intervals. And then we need to check against the general rules and make use of the water table. So some of the general rules for contours, the contours are gonna, they can't split and they can't merge. So the contour just has to be a single line, and it's gonna either, it's gonna go off of the map region, like all of these would, or it could close on itself. So you could have a closed contour. That's fine. But what it isn't gonna do is this. It's not gonna do that. It's not gonna just end. Can't do that. And you can't have it do that, you can have it split. So those are just basic rules of contouring. Here, this I think is also part of your handout package. Has to go across the region, it can't merge, can't cross. They can't do this. You can't have it do this. That's a violation. And then there'll be rules that you have to obey for contours that are on the water table. And that would be a good thing to pick up next. Okay.